right, electrodynamics. Okay, so what we want to do now is we want to talk about how magnetic and electric fields interact. And we're going to start that by saying what happens to a current loop in a changing magnetic field or a changing orientation. So what we're going to want to look at is how to induce a voltage in a current loop. So basically what we're talking about is a loop of wire, say like this. And it's going to be in a magnetic field like this. So we've talked about this a little bit before. We've talked about the torque on that wire. We've talked about that in terms of just, the torque. We've talked about that in terms of a motor. In this case, this guy's not going to move, or he could move. But what we're going to talk about is what happens when we try to put a with anything in it. All right, howdy. Now it's time to start the fourth unit, I guess. We got 5 units here. The fourth unit is electrodynamics. So we've talked about electric fields, we've talked about magnetic fields, and electrodynamics talks about how they interact together. And you might guess by the title, electrodynamics, what that means is that changing one of these fields is going to do something to the other field. And that's exactly what happens. So we'll talk about this. We'll eventually go through some other things and end up with electromagnetic waves. And basically that's all going to come back to the idea that when you change one field, you'll change the other, right? We'll talk about that this time in terms of a current loop. So we'll have a loop like this. And actually it's not a current loop. It's just a loop of wire. And it'll be in a magnetic field B. But now rather than what we've done in the past, this is going to induce a current in the wire. So in the past, what we've done is we've put a current through this wire, and that's given us a magnetic field. This produces a magnetic moment, and that magnetic moment produces a magnetic field B. Right? So that's one thing this does. We've also looked at the torque that can happen if you have this current in this wire and there's a magnetic field here. The wire is going to want to align with the magnetic field, right? And we've also looked at a motor, right? And so a motor took that last effect and it turned it into something useful so you can do physical work with it, right? So we've gone from having an electric control, that current, into a physical realization, a mechanical realization of the motor, which will give you rotation, which we can use with friction to wander around town with, right? So we looked at all that. Now we want to look at the opposite effect, which is if we can use a current to produce a magnetic field, how do we use a magnetic field to produce a current, right? And that is going to require a changing magnetic field. So we're not really ready for that. What we're going to talk about first is the flux through this thing. So what is a flux? Well, think a little bit about a pipe, right? So for that pipe, what we have inside of the pipe is, water, right? So we have all these little water molecules in the pipe. They're all moving at some speed v. And then let's say we have 2 surfaces. We can say we've got this, and we're going to just count every single piece of water molecule that goes through this gold loop. And then we have this silver loop, which is at an angle, right? So if you count the number of water molecules that go through those for, let's say, a second, what's the difference between those two? This one's at an angle, so it has a larger area. Does it get more water molecules going through it? And the answer is no, because they still have to go through the same slice, right? So it doesn't matter how you're measuring it. you're going to end up with the same number of water molecules going through each. That's the flux. That's the flux of molecules passing through that point in the pipe. This time what we're going to do is we're going to talk about what that means for the magnetic field. So for the magnetic field, we're going to take that and we're going to talk about the magnetic flux, right? And the magnetic flux through a loop is the area of the loop times the perpendicular field. Okay, so what do I mean by a perpendicular field? Okay, I mean that if this is your area, right? Here, this is your area, in there. Then, if you took the perpendicular direction to the loop, like you do this way, right? This is coming that way. What we care about is the magnetic field in this direction, right? So we can add, call that, oops, be perpendicular. So you can always create two different directions. This is perpendicular to the loop, and this is parallel to the loop this way. We only care about this part. This is the part that's going directly through that loop, right? In the same way here, we only care about going this way over here. Or we could say the effective area is the same because it has the same area in the cross section. So that's the part of the loop we care about, or part of the field we care about. So that's our flux. Phi equals A B perpendicular. Another way to say that is the area of the loop times the magnetic field times the cosine of the angle between them. Right, so this is theta. There. All right. So that is what we'll start with. We'll use this next time to figure out the change. What does it mean when we say the change in flux? How do we get changes in flux? What sorts of things do that? And after that, we'll talk about the rate of change. Okay, after we've talked about what it means just for the flux to change, what sort of things will make the flux change. All right?